All right, so students, what we're going to look at, this is when the fun begins. I know you've been looking forward to this. So this is integration by parts, where you have to do it more than once. So the problem's not complicated, but it can be kind of long and drawn out at times. So what I want you to notice about this integral is it's got pieces, particularly this sign, where the derivative is going to alternate. You know, derivative of sine is cosine. Derivative of cosine is negative sine. It's going to go back and forth and kind of rotate. So this is a typical kind of thing that you look for on this type of a problem. First of all, what we got to do is decide what we're going to work with as far as the integration by parts. So we got to figure out what we're going to let u be equal to and what dv. Okay, so what I'm going to do is I'm going to choose to do the derivative of e to the x. So I'm going to start this off by saying e to the x is going to be this piece right here. Okay, and then that will leave dv to be what's left over. And remember, what we've been trying to do is dv needs to be something that's pretty easy to integrate. So it's easy to integrate the sign. And du is something that's pretty easy to differentiate. Now you could probably try this problem both ways. Let's go with it this way, all right, and see kind of where this leads us. All right, so to begin with, du is just going to be the derivative of e to the 2x, which is itself. And by chain rule, the derivative of the exponent is 2, so that gives 2e to the 2x. Okay, and then v is going to be the integral of sine x dx. Okay, so what is that? That is, be careful, that is negative cosine of x, like that then. So the derivative of cosine is negative sine, so this would check out. Okay, so we're ready to roll with integration by parts then and just sort of see where it leads us. So by integration by parts, the formula is going to go like this. We have the integral of e to the 2x sine of x dx. Remember, we do u times v. So u times v is going to be negative e to the 2x cosine of x, and then minus the integral of v du. So we're going to multiply those two things out. That will give negative 2e to the 2x cosine of x times dx. Okay, I probably should have put my dx in there, like that. Okay, so now I'm all set up. So I've done the integration by parts formula. So I've got everything put in there correctly. Now I need to just probably clean this up a little bit and see where it leads then. All right, so let's see. I'm going to bring this down, and this is going to be e to the 2x cosine of x. Okay, that's a plus, and then that 2 could come out. So I'm going to write that as plus 2 times the integral of e to the 2x cosine of x times dx. Okay? Well, what we're running into here is this integral right here. It looks like you'd have to do it by integration by parts again, and you do. Okay, that's a perfect example of a parts integral. So what I'm going to do over here is we're going to do integration by parts again. Okay, so I'll kind of go over to this third step here, and I'm going to work with this again, just putting this together. So what I'm going to have is I'm just going to write down the integral that we're working with is e to the 2x cosine of x times dx. So we're going to start all over again. All right, so what I'm going to do is I'm going to let u be this part. Okay, so that's going to be e to the 2x. And then I'm going to let dv be the other part, pretty much the same thing that I did in step 1 of this problem. So I'm going to do this. I have cosine of x times dx. All right, and I'm going to put it all together again. All right, so what's du? Du is the derivative of e to the 2x, which is 2e to the 2x. Okay, what's v? V is the integral of cosine of x dx. Well, that is just the sine of x. All right, so we got everything set up to do integration by parts then again. So here's what I'm going to do with this. Now I'm going to go back into my main problem here. I'm going to kind of keep bringing this stuff down here. So I've got e to the 2x times cosine of x plus 2. Now this whole thing right here is going to get replaced by the parts formula over here. So I'm going to do u times v. So that's going to be e to the 2x sine of x. And then I'm going to go minus the integral of v du. So that will be 2e to the 2x sine x. Whoops. Thinking ahead there. Okay, so it's sine 2e to the 2x sine x times dx. Okay, like that. I should have put a dx right there. Okay, so that's what we end up having. And then we're going to kind of roll with this and see where this takes us then. I think when I was putting this together too, I may have left off my negative here. Let me make sure. Yeah, u times v, that's negative right there. So I want to make sure I got everything correct and don't mess up on anything here. All right. So now what I'm going to do with this then, so I'm going to go ahead and just kind of keep working with this and see where this leads us then. Now, one of the things I'm going to do here is I think it's real important to write the whole equation. I'm going to go ahead and bring this down. You don't want to forget about what we're originally trying to do. Okay, so that's the integral that we're working on. So I'm going to bring that down and I'll show you kind of what happens on this then. So bring everything down. That's going to be negative e to the 2x cosine of x. And what I'm going to go ahead and do is distribute that 2 through here. So I get 2 e to the 2x sine of x minus 2 here. Now, what I'm going to do is bring this 2 out also. So when I distribute and do 2 times 2, I'm going to get 4 times the integral of e to the 2x sine of x dx like that. All right. Now, look real carefully at what happened on this. Okay, what you want to notice is this thing here and this thing there, those are the same integral. Now, that's what we're trying to find, too, is we're trying to evaluate this integral. So we have an equation with integrals in it. So we can solve this equation for this integral. So notice what I'm going to do is I'm going to take this whole entire thing right here, and I'm going to move it to the other side of the equation. So I'm just going to write this down, bring this down. So that's e to the 2x sine x dx. And then when we move this over, that will become plus 4 times the integral of e to the 2x sine x dx, like that. And then we're going to leave this stuff where it is. So we're kind of putting the integrals together on one side of the equation. Everything else we just leave where it is. All right, so we're solving an equation with an integral in it. So that's negative e to the 2x cosine x plus 2e to the 2x sine x like that. All right, are you with me? Okay, that's the whole key. So what happens is when you do integration by parts more than once, you're trying to see if that original integral will pop back up in the problem so you have an integral equation you can solve for. So now notice, these are like terms. They really are. So you would have 4 and 1 would be 5. So what we're going to have then is we're going to have 5 times the integral of e to the 2x sine x. And that's, of course, what we're trying to solve for. All right. And then that's going to be equal to negative e to the 2x cosine of x plus 2e to the 2x sine x like that. All right, we got an equation to solve, and then we are basically done with the problem then, see? Okay. So what I can do here is I can multiply both sides of this equation by 1/5. So I'm going to multiply that whole side of that equation by 1/5. Then I get the result I'm looking for. So I've got the integral of e to the 2x sine x dx, which is what I was trying to integrate. Now I'm just going to distribute that 1/5 through there. So I would have negative 1/5 e to the 2x cosine of x plus 2/5 e to the 2x sine x like that. Okay, and then I can do a little bit of algebraic simplification to that And so what I'm going to go ahead and do, I think probably it would have been wise if I just factor stuff out. If this is an okay answer, there's nothing wrong with that answer right there. I'm just going to go ahead and take out common factors. So I've got e to the 2x that comes out. Then I could take a fifth out. In fact, I'm just going to take negative 1/5 e to the 2x out and factor it that way. All right, so that means that you would have a cosine of x left here. Okay. And then here you would end up having minus 2 sine of x like that. There's more than one way you can write the answer to that problem. So you can write it like that. You could have written it like this. This is the same thing as just 1/5 e to the 2x, 2 sine x minus cosine x. That's what you would get if you didn't take the negative 1/5 out of there. So it doesn't really matter. I just generally, if the first term has a negative in it, I just take it out. Okay? So that's it. That would be the answer to the problem. And you could certainly check that by doing a derivative. So the idea with this is, in your integral equation, after you go through 2 rotations of parts, these 2 things show up. Okay, and that's what happens. Now, parts, sometimes you can do 3 or 4 times. We're going to focus mostly on this happening 2 and probably not more than 3 times when you do these problems. Okay, so that's pretty typical what happens, all right? So to me, the key is how you write your steps. You got to be real clear in your step writing on this. Okay, so let's go to the next one. I'll do another one where we do parts twice. And this one kind of works out a little bit different way. And again, if you want to use this Lipet diagram on here, this kind of tells you the highest priority for u. So you choose u, the highest priority is a logarithm. So that would be your u right there, according to this diagram. So let's start by getting everything set up. So u is going to be the logarithm, and I'm going to write that as ln of x to the second power. And then you want to choose dv. dv is what's left over. And you always want to make sure that dv is something easy to integrate. So in that case, you have x to the second dx. Okay, so that's how we're going to start it. du, we need to do the derivative. By chain rule, that would be 2 times ln of x to the first power times the derivative of what's inside is 1 over x. So I would end up getting du is equal to 2x ln of x times dx. Okay, and then we got to do v. So v is the integral of x to the second dx. So you want to get that done. All right, so what is that? By power rule, that is x to the third over 3 would be v. Okay, so we got everything we need. We got this is u, this is dv, this is du, and that's v. Okay, so now what we're ready to do is we're ready to just use the parts formula then. Okay, u times v minus integral v du. Okay, so it's going to go like this. So the integral of x squared ln squared x dx is going to be equal to, we do u times v, so we go that way. So that looks like, I'm going to write that as 1/3 x to the third times ln of x squared, like that. God. Okay, so I've got, let's see, u times v, so I got that okay, and then minus integral of v du. All right, so it looks like we've got v is x to the third over 3, du is 2 over x times ln of x times dx. Okay, let's just kind of clean this up a little bit. So I'm going to write this as 1/3 x to the third. I'm just going to write that back as ln squared of x. Use that shorthand. And over here, what would happen is 2/3 could come out of the integral. So you'd have 2/3. And then x to the third over x would be x to the second. So you would have the integral of x to the second ln of x times dx. Okay, with the 2/3 coming out. Okay, so what are we into here? So we've made it through 1 rotation of parts. Now what we have is this looks like integration by parts again. Okay, so you still got that product, you still got that structure, So what I'm going to do over here is we're just going to go over and we're going to do parts again. Start all over again. Okay, so we're going to do the same kind of idea here. So again, with Lipet, u is going to be the ln. So we're going to do u is ln of x. And then dv is going to be what's left over, which will be x squared times dx. Okay, so we're ready to get everything put together then. Okay, so what's du? Du is the derivative of ln x, so that is 1 over x. V is the integral of x squared of dx, so what's that? That's x to the third over 3. Okay, so we're going to put this together, and if we go u times v minus integral of v du, we're going to get 1/3 x to the third ln x minus the integral of v du, which would be 1 over x times x to the third over 3 times dx. I've been kind of sloppy in forgetting to put that dx on the du there. Okay, so what do we have? We have 1/3 x to the third ln x minus, and then that will cross out and give 1/3 x to the second times dx, like that. And what happens is that's an integral you can do. So what I'm going to do here is, going back into this problem, this thing right here is this. So we're going to substitute back in. We have to kind of keep track of stuff as we go through this then. So I'm going to just go back to where I was and see if we can finish this up now. So I'm going to bring this down. That's 1/3 x to the third ln squared x minus 2/3, okay, and then put the rest of this stuff in here. Okay, so that's going to be 1/3. So I'm just replacing this whole thing right here, okay, with this whole integral with this. So it's 1/3 x to the third ln x. I'm going to bring that out, or you can do that in your head. 1/3 the integral of x to the second dx, like that. Okay, so that's where we are then. Okay, so let's finish this up then. So we're going to bring everything down. 1/3 x to the third ln squared x minus 2/3 1/3 x to the third ln x minus 1/3. Of course, that is going to be x to the third over 3, like that. So that takes care of that integral, and then don't forget your plus c at the end. All right, so I'll keep doing this because simplify as far as we can. That's going to be 1/3 x cubed ln squared x. I'm going to go ahead and distribute now. So that would be minus 2/9 x to the third ln x. And then this part right here, you would have a plus. So 2 times 1, and then 3 times 3 times 3 would be 27. X to the third plus c. So that should be the result of that problem. Okay, and that's a good way to write it. You could factor the x to the third out. You certainly don't have to on this problem, but you could take out a 1/3 and an x to the third in there, and you could write the answer like this. So then you would have a ln squared x minus 2 ln of x, and then plus a 2 plus c. Okay, and there's a couple of things that so you can write that answer either of those two ways. All right. Okay. All right. So see, the key on that is getting everything carefully written out. To me, that's what you have to do when you integrate by parts twice. Okay. All right. So I'll move to the next thing here. Now, what this is saying is if you're doing integration by parts for definite integrals, then what you can do is, when you do this UV part, you can just go ahead and evaluate, because that's the part of the result of the integral. Then you go ahead and do this integral right here. All right, so that just means once you get the UV, then evaluate it, and then this part right here, you got to do the same thing. Okay, so we're going to go and do a couple of definite integrals to finish this section up then. Okay, so on the next example here, let's see, we have a natural logarithm on here. So we'll set this one up. This is a good example of another integration by parts integral. Okay, remember, choose U, log is the way to go. And the idea with that is it's difficult to do that. Okay, it's hard to integrate an ln. So what we're going to do is U is going to be ln of 2x. Okay, so we got that part. dv is going to be what's left over. So dv is going to be 2x dx. There we go. Okay, and do the typical thing. So what's du? Du by chain rule, the derivative of a logarithm is 1 over the function times the derivative of the function inside. So that would be that. So du, don't forget the dx, that would be 1 over x times dx. Okay, so we got that. Okay, v is just the integral of d to the x, integral of dx, which is x. Okay, all right, so here's what we have. Here's u, here's v, there's dv, there's du. Okay, so now we're ready to put this thing in the parts formula, which is u times v minus the integral of v du. Okay, so then this is going to go like this. So when we go ahead and do this, I'm going to just put this together. So we have u times v, that looks like that is x, ln of 2x, minus the integral of v du. So that would be x times 1 over x dx like this. All right, and we're just going to work this out. Now I'm just working out the definite integral right now. I'm going to show you a couple of ways that you could go about doing this. So kind of an alternative approach I'm going to do on the side. So you could do this x ln of 2x. You could take that thing and evaluate that from 1 to e. And then this thing, of course, the x's cross out, so that would just be, excuse me, integral of dx 1 to e. So I'm going to show you two ways to kind of complete this problem. So the first way I'm going to do this is I'm just going to bring this down and focus on the indefinite integral. So I'll do that. Okay, so that's going to give x ln of 2x, and then the integral of dx is x, so we have that. Okay, and then step 3, what I'm going to do is I'm going to evaluate, and I'm going to show you the two ways that you could go about doing this. They're the same thing anyway. So if we did this way, our antiderivative is x ln of 2x minus x, and then we're going to evaluate that from 1 to e. Okay, so we just use fundamental theorem of integral calculus. So plug in the e, so we'll have e ln of 2e minus e, and then subtract, now plug in the 1, so that would be 1 times ln, 2 times 1, minus 1, and then just crunch out the details. So this looks like e ln of 2e minus e, and this is going to be minus ln of 2 minus 1. Okay, so that looks like e times ln of 2e minus e minus ln of 2 plus 1. Okay, now there is one thing that you can do, and you don't want to overlook these kind of things, because when you deal with this part right here, there's one other little thing you can do on this. So that thing, remember, if you do a log of a product, that is the sum of the logs. So I'm going to go ahead and break that up like this, and then see if that simplifies this a little further. Okay, so what we'd have is, of course, ln of e is 1, because e to the first is e. So we have e times ln of 2 plus 1 minus e minus ln of 2 plus 1. All right, distribute this out. That's going to be e ln 2 plus e. So you're going to end up getting the e's canceling out, it looks like. So we get this. The e's cross out, so it looks like we get e times ln of 2 minus ln of 2 plus 1. And to me, that's okay if you stop there. You could also, what I think you could also do is factor out an ln2 just out of this part right here. And then you could get and write this answer as ln of 2 times e minus 1 plus 1. So either of these two answers is fine. Okay? So that's how you could do that. Now, the other thing that you could do, I was going to show you, and it's kind of up to you how you do this. A lot of times once I get the antiderivative, I evaluate it. The theorem on the previous page is basically saying this part right here is a part of the integration by parts. So this UV part right here, you can just go ahead and evaluate it. And then we can do this integral here. I mean, you're doing the same thing. So let me just show you what would happen. If you did it this way, you would have E ln of 2e minus 1 ln of 2 times 1. Okay, and see, this would be whoops. Come on. Then have the minus sign, and then this would be the integral of dx is x, and you evaluate that 1 to e. So I'm just going to show you that you're doing the same thing. So this would be e times ln of 2e minus ln of 2, and then this would be e minus 1. So you would have e ln of 2e minus ln of 2 minus e plus 1. So I'm not going to finish this because I want you to notice that if you look at this, see how we're getting pretty much exactly the same thing here. Okay, so you would end up getting the same thing on this. And again, you could just go e ln 2 plus ln e minus ln 2 minus e plus 1. You're going to get exactly the same thing. All right, so this is just e times ln 2 plus 1 minus ln 2 minus e plus 1. So this is e ln 2 plus e minus ln 2 minus e plus 1. The e's cross out, you get exactly the same thing. Okay, e ln 2 minus ln 2 plus 1. All right, so you can do that either way. Okay, I usually just go this way. All right. Okay, so I'm going to do one last one here. I guess the other thing I wanted to do on this is just, since it's a definite integral, we might as well just check the answer and see if we've done this right. So let's go ahead and just do that real quick, just kind of as a quick reminder. So you just graph the ln of 2x is what we integrated. Since we're going 1 to e is 2.7, so I would just say go 0 to 3. It's always a good idea to go a little bit below and a little bit above the limits of integration. And then you can just sort of pick whatever you want to for y. Okay. Let's see. Let's change the window. Maybe let's do something like this. Let's say like maybe -5 to 5 on the y-axis. So we do that. Now we can go like we've learned. Second trace, option 7. Lower limit of the integral is 1. Upper limit is e. E is above the division key. So you do that. And then we get this graph then. Okay. So you can kind of look at what I have here. I used a different window on that, so I got that. Then if you take the answer, ln 2 times e minus 1 plus 1 on the calculator, these things will match up. So that's the numeric answer to the integral. That's the answer we got. So you can match those two things up. Okay? All right, very good. Okay, so I'm going to look through one more example. I just hadn't done much with the inverse trig functions, so I'm going to go ahead and do that. I kind of already got my graphs up here, so let's go through how you would do this last example then. Okay, so again, we're going to look at integration by parts. So the highest priority on this is inverse trig is a high priority for u. So it looks like according to this set of guidelines here, that would be your best thing to let u be equal to, and then dv will be what's left over. Okay, so let's go ahead and start integration by parts on this then. So u is going to be the inverse tangent of y to the second. dv is going to be what's left over, y dy. So it's easy to differentiate an inverse tangent, and it's easy to integrate a y dy. Okay, so du, so here is the rule, and you're going to start seeing this quite a bit in this class. When you differentiate an inverse tangent, it's 1 over 1 plus whatever that thing is there squared. Now this is going to be a chain rule here, so you want to be kind of careful. So this is the argument of the inverse tangent. So that's what's going to plug in there. So your derivative is going to be 1 over 1 plus y squared squared times the derivative by chain rule 2y times dy. So that's what that is. And then we'll clean that up a little bit here. So that looks like 2y over 1 plus y to the fourth times dy. Okay? And then dv, of course, v is just going to be the integral of y dy. So what's v? That's y squared over 2. Okay, so now we've got what we want. There's u, there's dv, here's du, there's dv. Okay, so we're now ready to put this in integration by parts. We're doing u times v minus the integral of v du. Okay? And let's see what happens. Now this one's got, I think, a lot of arithmetic involved on this, but I don't think you have to do this one twice. So let's just put it in the formula. Let's see where this leads us then. So u times v is going to be, we can write that as 1/2 y squared times inverse tangent of y to the second, like that. And then minus the integral of v du. Let's see. So v is 1/2 y squared. Du is this thing. So that's 2y over 1 plus y to the fourth times dy. And we'll want to kind of clean that up a little bit. So let's write what we got. So this is all put together. 1/2 y squared. Inverse tangent of y to the second. Minus, and notice the 2's cross out. So we'd be left with the integral of y to the third over 1 plus y to the fourth times dy. Okay? So there's several things that you could do here. And I want to just sort of pause here in a minute. So now the next thing we have to focus on is how to do that. Okay? Now what you could do right here, if you wanted to, is you could go ahead and evaluate this from 0 to 1 over square root of 2, or you can wait till the end. It doesn't matter. I usually just wait till the end. So I'm going to go ahead and focus on this thing right here and get this put together. So this looks like a U-substitution integral. So I'm going to go over at the side, and we're going to do a U-sub on this integral. So let's think about what the limits are going to be too. So 1 over square root of 2, and we're doing y cubed over 1 plus y to the fourth dy. So we're going to do that by U substitution. And let's see how we're going to do this then. Okay, so what we could do here is, let's see, it looks like you let u be the denominator, 1 plus y to the fourth. So du would be the derivative of that, which is 4y to the third dy. Okay, so again, this is going to be u. We have that taken care of. And then this part, we need to just work with the 4. So I would just divide both sides by 4. So I get 1/4 du is equal to y to the third dy. Okay, now you can go ahead and either work with the limits now. You can change the limits now if you want to, or you can wait till later. Okay, so I think I'm going to go ahead on this, and I'm going to go ahead and just change the limits here and do it this way. All right, so what I'll have here then is, let's change the limits. Okay, so the upper limit is 1 over square root of 2. Plug that into your U substitution, so you'll have 1 plus 1 over square root of 2 to the fourth. So that's going to be 1 plus 1 over, and see, the square root of 2 to the fourth is the square root of 16. So that would be 1/4. Now if you put that together, that's 4/4 plus a fourth. So that becomes 5 over 4. Okay, so we can go ahead and do that then. Okay, then I'm going to change the other limit. 0 is the lower limit. Again, plug into the U sub, so that's 1 plus 0 to the fourth. So that's equal to 1. So these would be the new limits of integration. Now what I'm going to do is I'm going to go back to the original problem and kind of show you how you could do this now. So let's write down the 1/2 y to the second inverse tangent of y to the second, and then that's going to be evaluated from 0 to 1 over square root of 2. Okay, like that. Okay, and then this part right here, well, our U-substitution on this is just going to be this. The y to the third dy is 1/4 du, and then u is the denominator, and we're taking that from 1 to 5/4. Okay, so I'm just going to put that integral in, so that is 1/4 times the integral, 1 to 5/4 of 1 over u times du. Okay, so I'm going to go about doing it this way. There's different ways you could do this. I mean, you could plug the u back in after you do this u sub integral and evaluate it from 0 to 1 over square root of 2. To me, it's probably just as simple to just go ahead and do it this way then. All right, so let's go ahead and start getting everything evaluated then. Okay, so this would be 1/2. The upper limit is 1 over square root of 2, and we're going to square that. Then we have inverse tangent of 1 over square root of 2 squared, like that. Then we plug in the 0, so that's going to be 1/2 inverse tangent of 0 to the second. Okay, like that. And let's see, I think I forgot to put my y in, so I got to correct that. Okay, so let's see. The y goes in there, the 0 goes in there, so it's 1/2 times 0 times inverse tangent of 0 to the second. And that's nice because that'll cross that whole thing out then. Okay? Then what you get here is this integral is just going to be 1/4. The integral of 1 over u is ln of natural logarithm of u, and then that gets evaluated from 1 to 5/4. Okay, so a couple of things you notice. That whole thing goes to 0, so that's nice. Work this out. This is going to be, and I don't really need the brackets anymore, so I'm going to have here, I'll have 1/2 times 1/2. You square the radical, it goes away. Then you'll have inverse tangent of, again, that'll be 1/2, like that. And then over here, we'll have 1/4. Plug in the upper limit, you'll have ln of 5/4 minus ln of 1. Okay, like that. All right. So what I have here is this would be 1/4. Now the inverse tangent, okay, well, 1/2 at pi over 4, you've got to think about your unit circle. At pi over 4, you have root 2 over 2, root 2 over 2. And since the tangent is y over x, notice that y over x here is 1. So we're trying to look at the inverse tangent of 1/2. Well, the inverse tangent of 1/2 is not going to fall on the unit circle. So you're going to end up leaving that alone then. So notice if I go inverse tangent of 1 over 2, I just get, decimals. So it's an irrational number. I think I'm probably in degree mode right now. I don't want that. I need to go ahead and put myself in radian mode. But the point is, you can't evaluate that on the unit circle. So we just leave that alone. For some reason, I was thinking about pi over 4, but that's not right. So I caught myself on that. So you just leave that alone. And then we'll kind of see what we're left with. So we have inverse tangent of 1/2. Okay, now when we simplify this, let's see, we could write this like this. We could write this as ln of 5 minus ln of 4. That's how you handle a log of a fraction. The ln of 1 is 0. Okay, so it looks like I would have 1/4 inverse tangent of 1/2. Now I can distribute through this now on this, and I would get minus 1/4 ln of 5 plus 1/4 ln of 4 like that. And there's several ways that you could write that answer. You could even just leave this as 5/4 if you want to. So, I mean, this would be okay. Or you could even just kind of go through it at this stage right here. And you could probably, if you wanted to, you could also write this like this. You could write this as 1/4 inverse tangent of 1/2 minus 1/4 ln of 5/4. Okay, so it could also be put together and just written that way. All right, so it doesn't really matter. And you could factor out the fourth as well, so there's a variety of ways you could write that answer. So you could write it that way too. So I'd be okay with this, I would be okay with that, and I would be okay with 1/4 parentheses inverse tangent of a half minus ln of 5/4. Okay, so any of those three ways you could write your answer. Okay, so that's how that would go. Now, as far as checking the answer graphically, I was just going to kind of show you what I did here. So, again, what you can do on this, you want to make sure you're in radian mode, and you just put it in your calculator like this. We're doing the graph of y inverse tangent of y squared, so use x. It's still going to do the same arithmetic. And then inverse tangent of x to the second, like that. Let's see, we're going 0 to 1 over square root of 2. Okay, so let's go 0. 1 over square root of 2 is less than 1. Let's go 0 to 1. Maybe scale that by 0.5 or something. And let's see, on this, I think I'll go like 0 to 1 or something like that. Or maybe even 0 to 0.5. I'm just going to mess with it a little bit and see what I get here. Okay, that's a pretty good looking curve right there. So it's a little different what I had here. So I think what I probably did is I did maybe 0 to 1 by 0.5 or something. I don't know. Okay, there we go. All right, so now we just trace it out. So you go option 7. Lower limit is 0. Upper limit is 1 divided by square root of 2. And it should give that area. Okay, so that's what I've got here. And then you can just check the answer that you got. It doesn't matter what form you want to put it in. Let's put it in this last form here. So 1/4 is 0.25. And then I'll have, come on, 0.25. And then parentheses inverse tangent of 0.5, a half is 0.5. And then minus natural logarithm of 5 over 4. And let's just see if that gives the same thing. And it does, okay? So we have done that correctly. So it's checkable, like all of your definite integrals are. Okay, so I did some of these problems a little bit differently than I did on the answers, the solutions that I put on Canvas. That's okay. It's okay to show you just little different nuances in how you do the problem. So integration by parts is real important, and you'll be doing this throughout the rest of the semester. Again, the key thing to learn is generally you're looking for an integral where you have a product of two functions. Parts is generally a good way. Use this LIPET as a way to help you, as a guideline to choose U. And when you do integration by parts 2 or 3 times, just be careful about how you write your steps. That's real key. All right, good luck. Have fun.